Welcome to today's explainer. We usually look up at the night sky and see this calm, peaceful canopy of stars. It looks so static, right? But the data actually tells a completely different story. Today, we're going to treat the universe like a true crime forensics file. We're going to look at a very specific set of clues left behind by a massive cosmic collision that literally shaped our own Milky Way galaxy. Let's dive right in and break down exactly how scientists act as galactic detectives. Okay. To find our prime suspect, we have to travel exactly 35,900 light-years away, deep into the Centauros constellation. If you look at this region of space, you'll spot what looks like a totally ordinary collection of stars, which astronomers call a globular cluster. At first glance, a cluster at this immense distance seems like just another quiet, sleepy neighborhood out in the vast suburbs of our galaxy. But I promise you, that massive distance hides a much deeper and much more ancient secret that is just waiting to be decoded. And here is the scene of the crime, Caldwell 84, which you might also hear cataloged as NGC 5286. It was actually first discovered way back in 1826 by the astronomer James Dunlop. Now, see those gray and black dots? Those are plotting out stars that are actually moving together as one single group, distinguishing them from the random background stars. For the longest time, this cluster was incredibly hard to study because thick space dust, what astronomers refer to as foreground reddening, totally blocked our view. But as modern telescopes focus on those specific targets highlighted in red and black, Caldwell 84 is finally opening up about its extremely violent past. So when astronomers zoomed in to do a sort of chemical autopsy on the individual stars in this cluster, they found things that simply shouldn't be there. We're talking bizarre chemical fingerprints. Normal globular clusters are usually pretty uniform, but here they found a super rare CN-CH positive correlation. They also spotted significant variations in iron and heavy enhancements in S-process elements, which are essentially just heavy metals forged in the hearts of dying stars. Ultimately, all these heavy elements point to one inescapable conclusion. This cluster actually contains trapped supernova ejecta. Just look at how the data breaks down here. Low-resolution spectroscopy clearly splits the red giant stars of Caldwell 84 into three totally distinct subpopulations. Notice the groupings? The blue dots are weak in these anomalies, but the red dots are heavily enhanced. This stepped, discrete distribution is an absolute smoking gun. It proves that we're looking at later generation stars that were heavily enriched by the violent explosions of ancient supernovae. But hold on, because this evidence brings up a massive question for our investigation. Normal star clusters simply aren't massive enough to hold on to the violent, incredibly fast-moving ejecta of an exploding supernova. The gravity of a standard globular cluster is just too weak. A blast like that should blow all those heavy elements right out into deep space. So if a standard cluster can't do it, how on earth did Caldwell 84 manage to trap this material and form those distinct, chemically enriched populations we just looked at? To solve this, we actually need a total shift in perspective. On one side, you have your normal Milky Way globular clusters. They formed right here in our galaxy and have uniform chemistry. But on the flip side, you have an anomalous clusters like Caldwell 84. The leading theory here is that Caldwell 84 isn't a normal cluster at all. It's actually the fossilized accreted nucleus of a former dwarf galaxy. Because it used to be a massive galaxy in its own right, it had more than enough gravity to trap that supernova ejecta before it was eventually stripped down to the dense core we see today. So, who or what destroyed this dwarf galaxy and stripped it down to just Caldwell 84? To figure that out, we have to track the orbital ballistics of the cluster using a physics framework called kinematic action space. I want you to think of action space like a cosmic flight data recorder. The orbital actions of a star cluster stay incredibly constant over billions of years, even while the rest of the galaxy shifts around them. By calculating these mathematical constants, astronomers can literally rewind the clock to see exactly where a cluster originally came from. And when we run that action space calculation for 91 different Milky Way globular clusters, a really striking pattern pops out. Look closely at the open black circles that mark our anomalous clusters. When we map their vertical and side-to-side movements, they are clumped tightly together. But right in the middle, mapping their radial, meaning their inward and outward action, they're strung out like beads on a chain. They share this highly distinct kinematic signature, which proves, without a doubt, that they were all dumped into our galaxy during the exact same cosmic event. That specific kinematic grouping, it completely gives away the culprit. We are talking about a massive merger event known to astronomers as the Gaia sausage. The Gaia sausage is the scattered remnant of a huge dwarf galaxy, weighing in at roughly 50 billion solar masses, that crashed head-on into the Milky Way. When we map out the velocities of the stars left behind by this collision, they form this highly irregular, elongated structure. This dwarf galaxy didn't just casually brush past us, it plunged directly into the heart of our galaxy on a strongly radial orbit. If you look at the velocity distribution here, you can literally see the elongated shape of the orbits that gives the sausage its name. Those black circles represent the globular clusters brought in by this massive merger, and that includes our prime suspect, Caldwell 84. Notice how stretched out that distribution is along the radial axis? Instead of moving in nice, neat circular orbits around the galaxy, their trajectories are stretched to the absolute extreme, pointing straight like an arrow toward the galactic center. Which brings us to a frankly staggering number, 0.80. The data confirms that Caldwell 84 and its kin are plunging through our galaxy on highly eccentric orbits measuring 0.80 or greater. Unlike native objects that just circle peacefully in the galactic disk, these clusters act like cosmic darts. They spend most of their time hovering way, way out at the very edges of the galactic halo, only to plunge violently straight down through the center of the Milky Way. It completely gives away their violent, accreted origins. As a final piece of forensic evidence, let's plot their age against their metallicity. Most of the Milky Way's native clusters, those gray dots, form a standard broad track at around 12.8 billion years old. But our Gaia sausage clusters, the black circles, form an entirely different, highly distinct track. This unique signature is exactly what you'd expect from a rogue dwarf galaxy that evolved completely independently out in the void of space before finally slamming into the Milky Way. Let's put this whole story together on a timeline because the narrative is just incredible. Billions of years ago, a massive independent dwarf galaxy forms. Over the next few million years, supernova explode inside it, slowly enriching its core with the heavy metals and carbon anomalies we see today. Then, boom, 8 to 10 billion years ago, this dwarf galaxy violently crashes head-on into the Milky Way. It scatters its outer stars to form the Gaia sausage and leaves behind only its dense core. Finally, jump to 1826, that quiet remnant core is spotted through a telescope by James Dunlop, and it eventually becomes known to us as Caldwell 84.
What we've uncovered today completely changes how we should look at the universe. By studying this one little, seemingly ordinary cluster, 35,900 light-years away in the Centaurus constellation, we've actually been able to decode the violent, collision-filled origins of our own galaxy. The structural clues left in the chemistry and the orbital mechanics of Caldwell 84 prove for sure that our Milky Way grew by consuming its neighbors. So I'll leave you with this question to ponder the next time you look up. How many other quiet clusters in our night sky are actually just the ghost cores of long-dead galaxies waiting to be discovered?